Hello, Math 1010. This is a video for section 6.5. In order to start, let's take a look at the binomials x minus 3 and x plus 3. Recall, in order to multiply those, we distribute through the x from one binomial to the other terms, and the negative 3 from one binomial to the other terms. That'll give us x squared plus 3x minus 3x minus 9. And then to simplify this, you may notice something a little interesting. The positive 3x and the negative 3x add up to 0. And so we have a 0 middle term, and it just goes to x squared minus 9. This is called a difference of squares. The difference is another way of saying subtraction. And then squares are something that have a number or variable that multiplies by itself to equal it. So if you take a look at x squared, that is x times x. And if you take a look at 9, that is 3 times 3. So those are perfect squares, and it is a difference of squares. Let's take a look at the 3 problems in practice A. So this first one is x squared minus 36. We go ahead and make our sets of parentheses. And we know we're going to need x here and x here in order to multiply to x squared. And then 6 here and 6 here in order to multiply to 36. And then because there's 0 middle term, we need to get 1 minus and 1 plus. And we can go ahead and check that. And that would be negative 6x and positive 6x. And those would add up to 0x, so that works. If we take a look at the next one, it's x squared minus 1. So we make our sets of parentheses, x and x. And then 1 is a perfect square. It's 1 times 1. 1's going to be minus, and 1's going to be plus. Looking at the next one, it is also a difference of perfect squares. So 4x squared is 2x times 2x. And 9 is 3 times 3. And then make 1 minus and 1 plus so that you'll get the 0 middle term when it gets multiplied out. And don't forget, on all of these, we should check for a greatest common factor before factoring further. And in fact, if we had looked for that on letter C, we notice that there was not a greatest common factor. So it didn't affect us. But let's go ahead and take a look at the 3 problems in practice B. So the first one is 20y squared minus 45. Let's take a look for any GCFs, greatest common factors. And I believe there is one. I think it is 5. So 5 can get factored out front, and we'd be left with 4y squared minus 9. And then if you look at what's in parentheses, we've got another difference of squares here. So we can make our 2 sets of parentheses. And the thing that multiplies by itself to equal 4y squared is 2y. And the thing that multiplies by itself to equal 9 is 3. Make 1 minus, make 1 plus. And then we also still have that greatest common factor of 5 that we took out originally. If we take a look at letter B, it looks a little different because it's got a negative leading coefficient. And if we look for a GCF, it doesn't appear to have one. However, whenever your leading term, your leading coefficient is negative, it is a good idea to factor out a negative. So pretend that the greatest common factor is negative 1. So if I pull out a negative, then I would have positive 25x squared. And then instead of positive 16, it'll be minus 16. And now that is a difference of squares that we have in parentheses there. So 5x and 5x will multiply to 25x squared. And then 4 and 4 will multiply to 16. 1 needs to be minus, 1 needs to be plus in order to multiply to negative 16 and in order to get a 0 middle term. And then don't forget the negative that we pulled out originally with the greatest common factor. If we look at letter C, There is no greatest common factor. So we move right to our two sets of parentheses. And then x here and x here. However, this one's a little different. It is not a difference of squares, it's a sum of squares. We've got an addition sign there instead of a subtraction sign. So sometimes we may think, okay, well, if it's just a sum, then instead of 1 minus, 1 plus, maybe they are both plus. However, we should check that. Let's go ahead and do it. 2 times x is 2x, and x times 2 is 2x. And those do not add up to 0. They add up to 4x. So we would have a middle term if we did that. So then sometimes we think, well, if we can't have them both be positive, then maybe one needs to be positive and one needs to be negative. However, we know that that is what a difference of squares factors to, right? This would be x squared minus 4. But the problem is x squared plus 4. So this one's a little tricky, and you can go back and forth like we've been doing. However, the reason why it's tricky is because it is not factorable over the real numbers. So a sum of squares is not factorable. When we have something that's not factorable, we call it prime. So that binomial right there is prime. Moving on, we can also have sums and differences of cubes that can be factored. So if a perfect square is the result of something being multiplied by itself, then a perfect cube is the result of something being multiplied by itself 3 times. So if you take a look at this box here, we've got some factoring patterns to help us factor sums and differences of cubes. It looks like a lot to look at, but let's just break it down bit by bit. So if you look on the left side, it says a cubed plus b cubed. That means something getting cubed plus another thing getting cubed. And that will factor to what's on the right side of the equal sign, which is just the something without the cube. So a without the power of 3. And then plus b without the power of 3. And then we've got a squared minus a times b plus b squared. And if you were to distribute the a through and distribute the b through, you would multiply it out, cancel terms, and you would end up getting a cubed plus b cubed. And it doesn't just have to work with the sum of cubes, it also works with a difference of cubes. Notice how it looks very similar, but some of the signs are different. So instead of a plus b, what it factors to, it's a minus b, and then a squared plus ab plus b squared. Okay, so even though, as we mentioned in the last problem C, where it was x squared plus 4, and we identified that you can't factor a sum of squares, you actually can factor a sum of cubes, and you can factor a difference of cubes. So let's take a look at example 1. This says y cubed plus 27. So what's happening here is we've got 2 perfect cubes. So we've got y, and it is getting cubed. And then 27 is the result of something being cubed. It's the result of 3 being cubed. You can find that out by taking the cube root of 27 in your calculator. So what this means is, in our pattern that has a's and b's, a is y, and b is 3. So if you look at the pattern up above, everywhere there's an a, I'm going to put a y, and everywhere that has a b, I'm going to put a 3. So therefore, we would have parenthesis y plus 3, parenthesis, and then y squared, because that's a, minus 3 times y plus 3 squared. And then we'll go ahead and clean this up a bit. We know that 3 squared, we can simplify that to 9, so let's go ahead and do it. So y plus 3 times y squared minus 3y plus 9. And that's where we would stop. That is the factorization of that sum of cubes. Meaning if you were to multiply it out, then you would get y cubed plus 27. If you take a look at practice C, it's similar. It's got r cubed plus 8. Let's identify what is getting cubed. So this is r getting cubed plus 2 getting cubed, right? 2 is the cube root of 8. So anywhere there's an a, we're going to put r. Anywhere there's a b in the pattern, we're going to put 2. So this will factor to r plus 2 multiplied by, in parentheses, r squared minus 2r plus 2 squared. And then let's do 2 squared to be 4. So we get a final result of this bottom expression right there. So that would be the factorization of r cubed plus 8. Let's take a look at the last examples. We are going to factor 16y cubed minus 2x cubed. So if we take a look at that one, the very first thing we should do, don't forget, is actually to look for a greatest common factor. And there actually is one. It is 2. If I take out a 2, then I'll have 8y cubed minus x cubed. So then inside the parentheses, we have a difference of cubes. So a, the thing that is getting cubed to equal 8y cubed, is 2y. And sometimes that's confusing because students look at a and think that it should just be equal to just one thing, like just a number or just a variable. But it can be equal to an entire term, which is 2y. So everywhere I see an a in the difference pattern, I'm going to put 2y. And then the b is just x. That's not too hard to see. So when we do our pattern, we're going to have the GCF of 2 out front, and then it'll be 2y minus x multiplied by, and then this is another common mistake that can be made. You need to put 2y in parentheses because that is what a is. A is the 2 and the y being multiplied together. And if you don't put them in parentheses with the squared, then you're only going to square the y, but the 2 should also be squared. And then in the pattern for the difference, it's now a plus sign. And so we'll put 2yx and then plus x squared. So we can clean this up a little bit to get a final result. We'll have 2 on the outside and then 2y minus x. And then this is where I can clean that up a bit. 2 squared is 4, and then y squared is just y squared. And then the others can just stay the same. And that would be the result for example 2. We take a look at practice D, and we notice that m is getting cubed first, so that's pretty easy to see that a would be m when we look at our factoring pattern. But then we might need our calculator to identify what the cube root of 125 is. And it turns out that it is 5. So b is both 5 and n being multiplied together. So in the pattern, when we've got a minus b times a squared plus ab plus b squared. Everywhere I see an a, I'm going to put an m. Everywhere I see a b, I'm going to put 5n. So we need to put parentheses around that for the last term so that when we square it, the 5 gets squared as well. So we'll clean this up a little bit to get a final result of m minus 5n times m squared plus 5mn plus 25n squared. And that would be the factorization of that binomial in practice D.